Hello students, next we shall move on to the next topic, that is complexes of alkali metals. So as we see, usually alkali metals, usually the complexes are found by some of the metals of 3D block element, that is transition metals. Here alkali metals and alkaline earth metals also forms complexes to some extent. Now we shall see how these complexes are found by using alkali metals and alkaline earth metal ions. Alkali metal ions, with the exception of lithium ion, have very little polarizing power due to their large size and only a unit positive charge. Yeah, that means all alkali metals of course, have a +1 positive charge. As a result, they have only a weak tendency to form complexes with unidentate ligands. However, alkali metal ions form reasonably stable complexes with some of bidentate and polydentate ligands such as salicylaldehyde, beta ketones, nitrophenols, alpha nitroso beta naphthol, and etc. Thus, when NaOH is added to a solution of salicylaldehyde, a neutral complex is formed which is soluble in organic solvents. So here you can see how the complexes are formed. So that is, a salicylaldehyde reacts with NaOH and forms a complex uh, which is soluble in only in organic solvents. It is a neutral complex of salicylaldehyde and NaOH. So below you can see how the anhydrous sodium derivative of acetylacetone takes up water to produce a hydrated complex which is also soluble in organic solvents. So these two are some of the complexes of with regard to sodium ion. So lithium ion, as we have already said, because of its little polarizing power and only unit positive charge, it doesn't form a stable complex. So wraparound complexes. What are these wraparound complexes? Wraparound complexes are nothing but the polydentate ligands such as crown ethers and cryptates are the most important ligands which form highly stable complexes with alkali metal ions. These ligands wrap the metal ions completely and protect them from coming into contact with the solvent. That means these complexes, they form only with the suitable a particular metal ion. So you can see how this it is selected. The cause of selectivity lies in the size of the hole. The hole is here should be understood as a space available in polydentate ligand of type mentioned. Only that alkali metal ion which exactly fits into the hole forms a stable complex. That means it is just like a lock on key. You can't open every lock with the same key. For example, the hole or space in cryptide 222 is just of the right size for the potassium ion to fit in, whereas lithium and sodium ions are too small to make contact with the oxygen atoms of the ligand, that is cryptide 222. On the other hand, rubidium and cesium ions are too big in size to fit in the hole. That is, similarly, sodium ion complex of crystal 221 is most stable out of all the alkali metal ion complexes found with this ligand. So all complexes, uh, that is complexes and, same ligand cannot form complex with all metal ions, or all metal ions doesn't fit a particular ligand. So or vice versa, you can understand. So particular ligand will form a complex with particular metal ion, that is where if the space available is correct in nature. So here you can see, so potassium ion forms a complex with cryptide 222, whereas sodium forms complex of crystal 221. So here they are given, there is crown ethers and cryptates, how these are formed. So these are crown ethers of alkali metals, or we can call them as wraparound complexes. First two one are crown ethers, the last one is cryptate. So where they are mentioned, these are oxygen atoms. So in last complex, M is metal and N is a nitrogen. Now we shall see how the complex formation with respect to alkaline earth metals. Beryllium, because of its small size, forms stable complexes with halogens. That is, for example, beryllium trifluoride and barium tetrafluoride. The complex ion beryllium trifluoride involves sp2 hybridization and therefore has a planar trigonal structure as shown in the figure 5.3 below. So in complex ion beryllium tetrafluoride involves sp3 hybridization, hence it has a tetrahedral structure. So 5.3 it shows a beryllium trifluoride structure, and 5.4 shows a tetrahedral structure of beryllium tetrafluoride complex ion. Beryllium trifluoride has a planar trigonal structure. Beryllium tetrafluoride has a tetrahedral structure. So complex compounds of beryllium with oxalic acid. Beryllium also forms a complex compound with oxalic acid. The complex ion BeOx twice 2 minus is known to have a tetrahedral structure. So this will be shown in the next figure, that is 5.5. Complex of magnesium. So this is very important complex. So as we know, magnesium forms tetrahedral halide complex of type C2H5,4N and MgCl4. The chelates of magnesium with EDTA and pyrophosphates are also known. However, the most important complex of magnesium is naturally occurring chlorophyll, the green pigment present in plants which photosynthesizes the synthesis of carbohydrates in nature from carbon dioxide and water. So that is chlorophyll pigment which is present in green plants has a metal, and it is also a complex where the metal ion present here is magnesium. So this you can see in the next figure. So that is structural of the 5.5 structure of beryllium oxalate, and next is a macrocyclic ligand involved in is derived from the parent tetrapyrrole molecule porphyrin. Structure of chlorophyll is given below here. So magnesium is a metal present here. It is also a complex surrounded by nitrogen atoms and tetrapyrrole molecule porphyrin ring. Complexes of calcium, strontium and barium are also known. Amongst the complexes of calcium, strontium and barium, the water-soluble complex of calcium with EDTA, that is most important because of its analytical application. That means the given here structure is, it is in calcium EDTA. As you know, if you are aware with ligands, so when you study ligands or coordination compounds, you will come to know what is EDTA. EDTA is an polydentate ligand, ethylene ethylene diamine tetraacetate, or you can call ethylene diamine tetraacetic acid ligand, forms a complex with a calcium metal. Here it is a polydentate. EDTA is an polydentate ligand. Ligands. So if you are aware with ligands are classified as monodentate if it donates say one pair of electrons towards the metal ion, bidentate if it donates two pairs of electrons towards central metal ion, so on, tridentate and polydentate. So EDTA donates many pairs of more than 4 pairs of electrons towards central metal ion. So this is regarding complex of alkali metal and alkaline earth metals. So thank you.